All right, hello everyone, and welcome to the Industrial Matrix from Time to Condition-Based Lubrication webinar. We're obviously brought to you by Industrial Matrix. So we have lots of people joining today. Attendees will not be able to see each other, so please feel free to leave a comment letting everyone know who you are, what your title is, where you're from, and as we're doing the run through the introduction. So a recording of today's webinar will be automatically emailed when we conclude today. If you wish to have a downloadable PDF copy of today's session, we'll be able to provide that upon request. We do recommend accessing this webinar through Google Chrome to ensure the smoothest access and viewing efficiency. Please note that we won't be able to hear you as the attendees, so please feel free to ask questions or comment or simply apply a thumbs up through the tab at the bottom of the main screen. You can post questions in the question box and we will either answer them in the chat or Ken will answer them live. We're also going to reserve about 10-15 minutes at the end of the session for an open Q&A period with Ken. So please feel free to send questions as they come up. So we will also be posting polls throughout the webinar to ensure that we know our audience and we can provide relevant information. So getting introductions. So here at Industrial Matrix, we provide leading edge condition monitoring solutions condition-based monitoring through the use of various wireless predictive technologies. Our system analyzes your equipment's rotational health and identifies early issues and predicts failures so that you can fix the issue before it takes you down. My name is Dan Follows. I'm the Global Director of Customer Success here at Industrial Matrix, and I'll be the moderator of this webinar. Joining us from the team, we also have Samuel Tomlinson, who's the Director of Sales and Marketing here at Industrial Matrix, and he'll be working with us to answer any sales-based questions. Last but not least, we've got Ken Mitchell. Ken is a Customer Success Manager and Technical Sales Advisor here at Industrial Matrix. He's got Cat 2 vibration, Level 2 ultrasound certification, as well as CRL certified. So with that being said, I'll hand it over to Ken, and you can take us away.
Awesome. Thanks, Dan. You can hear me all right?
Loud and clear.
Fantastic. Well, thanks everyone for joining us today. This is our first webinar here at Industrial Matrix, and we've chosen a topic that usually drums up a lot of interest, acoustic and on-condition lubrication. So that's what we're going to talk about today as everyone comes on. Like Dan said, do encourage, if you have any questions, utilize the chat feature in the bottom right. We'll open it up at the end, especially to answer any questions. We can also schedule some one-on-one time if anyone's interested in diving a little bit deeper into that. So with that being said, I'll start with an introduction. So for those of you who I haven't met yet, my name's Ken Mitchell. I've been working in this condition monitoring field for a little bit over 8 years now. Before that, I did spend some time as an industrial millwright, so kind of a well-rounded scope on working the tools and then starting to do condition monitoring. I've worked with different various industries from pulp and paper to gas and oil, among others, to help establish condition monitoring programs. Now, I got to say, I'm quite passionate about this technology. I really have seen it in my short time in this industry progress quite a bit. As technology grows, the ability to diagnose and ascertain the health of our machinery keeps getting better and better, from analog instruments 10, 15 years ago to online autonomous systems that we're getting into this day and age. As we look ahead, really the next generation of reliability is getting into that Industry 4.0 space, where we integrate with IoT and really give us a instantaneous indication of the health of our assets and really the condition of our machinery. So looking ahead, I mean, it's a very promising industry in the space that we're all living in or starting to get into. It's really rapidly changing, and I am very excited to be on board for this and then the next generation as far as what we have. So why are we here today? Well, I'll start with a statistic. Up to 80% of all bearing failures can be attributed to poor lubrication. Now, we pulled this from Plant Engineering. There's a lot of different numbers out there, but it's safe to say that poor lubrication practices are probably the biggest contributor to our bearings not reaching their L10 life, at least those greasable bearings. If we don't hone in on precision installation and proper greasing techniques, those are really the only two interventions that we can have with our machinery throughout the life, aside from operational and different engineering specifications. So getting a handle on our lubrication is really imperative to extend the life of our assets and make sure that we're getting the return on our investments, our assets, and really mitigating that unplanned downtime. So a couple screenshots on the screen of, cases of poor lubrication, from contamination to over lubrication to, grease blowing out seals and get into motor windings. We've all kind of seen it. So for today's agenda, I'm going to start by talking about lubrication practices. We'll take you through a brief history of lubrication. We'll talk about what lubricants do, how much grease goes into a bearing. That's kind of the age-old question. And then we'll build on that and get into condition-based lubrication, where we can really justify how much grease we're putting into a bearing. We're going to tie that in with ultrasonics, because that is a very important and critical technology for diagnosing and analyzing how much grease should be in a bearing. And then I'll get into some types of equipment as well, just to paint the picture of what's out there and how the industry is really accelerating and growing the options that we now have to grease based on condition. Then finally, we'll end off with questions and answers. So let's start off with a quick poll. Question for everyone in the audience: have you had any bearings fail in the past year due to poor lubrication? So Dan's going to queue up the poll. You should see it pop up on your screen. If you don't mind, please do participate. This one's pretty much a yes or a no answer. So I'll give a couple moments for everyone to tick that off. And then when you're done, you can go ahead and submit your vote at the bottom there. So I'm actually going to fill this out myself as well, based on my experience. And then we should have the poll in there. So in addition to that, if you've selected yes, or even if you selected no, how many bearings have you had fail in your facility or facilities that you're involved with over the past year due to poor lubrication? So again, you should see a question pop up on the screen right now for that next poll. And we'll go ahead and tick off as far as the number that we see. Let's go ahead and put that up on there. All right, so we start with 0, 1, 2, 3, 4 plus. So go ahead and select one of those options. Obviously, if you hit no on the last question, then that'll be your answer. So I'll go ahead and select one based on where I've been involved. So the numbers that are coming in, I don't know if everyone can see, we had about 75% of the audience answered yes to bearing fail in the past year due to poor lubrication. And then the numbers are kind of all over from 1 to 4 plus. So it definitely is a pain point throughout industry, and getting a handle on our lubrication is really the best way to do that. So lubrication practices, again, we'll go over a history of lubrication, what lubricants do, how much grease goes into a bearing, and then finally condition-based monitoring. I want to start with a question, and I always like to tie this into an analogy and tell a little bit of a story. So my question for everyone is, how much water should you drink in a day? Well, experts say we should drink anywhere from 6 to 8 glasses each day. Now, those needs can change. What if we're outside on a humid 90-degree day or 30 degrees Celsius running a marathon? How about if we're sitting at our desk like we are now attending a webinar? The point is, bearings are like us. Their needs change depending on their environment and their workload. The harder they work, the more that they need, just like our bodies and how we nourish ourselves. So keep that in mind as we go through this. Let's start with lubrication practices. So rewind the clock many, many years ago, BC, 17th century. The Egyptians got out there and they started to build pyramids and build structures. They realized that if they put stones on their sleds and slid them, it was really hard. So they needed a friction modifier. And they utilized olive oil. So they'd start to pour that under their sled and they could slide that along. And that was really the first instance of lubrication that we had in our world, where we could use some type of a medium to really reduce friction, dissipate heat, reduce wear. Fast forward a little while later, about 3 centuries, and the ancient Romans, they started to use animal fat to lubricate the chariot axles. If they didn't, they would heat up, they would fail. They also realized that they could spin a lot quicker. Now, fast forward many, many years later into the 1850s and into the 20th century, petroleum oils are developed, and they really become the industry standard. Somewhere around the 70s, we started to get into synthetic lubricants, which is kind of where we live right now. But we've been increasing on this, and the whole goal is to dissipate that heat and to really fight friction and reduce wear. So that is the 3 things that lubricants are designed to do, as well as prevent corrosion through the addition of additives. So what is grease comprised of? We have 3 basic compounds. There's a base oil, a thickener, and an additive. And what happens is, as we replenish grease into a rolling element bearing, we're going to start to use up that thickener. The base oil is going to deteriorate. The additives are going to be consumed. So we need to regenerate that process on a set schedule. And then the question becomes, well, how much grease and when do we do that? And that's really what we're going to get into. So to start with everything, if we have the best equipment out there, we grease based on condition, we're giving the bearing the right amount of grease that it needs, those things don't overcome bad lubrication practices. So we really need to start there as we start to build out a lubrication program and ensure that we're doing that precision lubrication. So it starts with storage. When we get that lubricant in, where are we putting it? Is it sitting in an open drum off to the side of a lube room, maybe with the cap off, where we can start to get those contaminants in there? And then when we go out to our equipment, are we picking the right grease? Are we ensuring that if we're greasing a bearing, that that's meeting the OEM specs or the conditions that we're running that equipment under, if we need a high temp grease or a lithium based grease? And then finally, when grease operates outside their operating temperature and speed ranges, when we put too much strain on grease, it can't stand up to the job. So we really need to start by making sure that we're storing our grease properly, we're handling it properly, and then we're putting the right grease under the right conditions into our bearings. No matter how much we hone in and how much on condition based lubrication we get into, this is really where it starts, is proper handling. So let's take you through a bearing. Well, what happens when we undergrease a bearing? That's pretty straightforward. We've all kind of been out there. We walk by a bearing, we can hear it rattling around. Yeah, that probably needs grease. It's getting due for that. Probably doing damage at that point in time. But inevitably, when a bearing runs dry on grease, we're going to start to use up that thickener, that base oil, and that's going to result in metal on metal contact. It's also going to degrade the grease. This picture that you see up on your screen, this is from a customer site that was just a poor lubrication practice when we started working with them. They had seals blowing out. They were using a low temp grease and a high temp application. And as you can see, it was really just chewing up that grease. It wasn't able to get into the bearing. So that was resulting in more heat, more friction, starting to burn up the grease. Now, just as bad as undergreasing a bearing, overgreasing a bearing can be almost as bad in some instances. When we overgrease a bearing, we're adding more heat, more friction. That bearing has to work a lot harder to fight through that grease and really do its job and rotate. We can also start to damage seals, introduce foreign contaminants, increase power consumption. These are all bad things that we don't want to do. Good analogy I like to use is you're in the ocean on vacation and you're walking through the water and the water's up to your shoulders. It's really hard to get through that water. Now, as you get closer to shoreline and say that water's just up to your knees, you can just kind of skip right out. Think of a rolling element bearing the same way. If we fill that up, that bearing's got to fill right up to the shoulders or right up to the top of that cavity. That bearing's got to work a lot harder to fight through it. Whereas we just put the right amount of grease in there, that bearing can spin along smoothly and dissipate that heat and treat that metal. So lubrication practices. Heard this before. How much grease do you put in that bearing? As I go into a plant or plants that I've worked in before, they go, we give it 6 pumps every 3 weeks, or we give it 5 pumps every 4 weeks. So you really got to start to ask questions. Well, what grease gun are you using? Because 6 pumps in one gun might not be 6 pumps in another gun. What if you have lubers on there, so on and so forth? How much is the output of that grease gun? Have you ever really checked it? Are you using the same grease every time, or is the lube tech or the technician responsible for that, grabbing one off the shelf and putting grease in because it's a bearing, any old grease will do, right? Now, what if you're not running as much? If you've got downtime, or if you come through seasonal cycles, or what about if you're running in the summer when temperatures rise? Your grease consumption is going to pick up. And then finally, where did that PM even come from? Sometimes we go into the computer or we go to our PMs and say, okay, well, it's there, so it has to be right. We really need to start to question where we're getting this information from, and that's going to allow us to better grease our bearings. So a couple more questions. Can we ever be 100% confident that we're adding just the right amount of grease? We know there's a sweet spot between under and over lubrication. And then how do we compensate for all these environmental conditions? Finally, what are the consequences of not adding the proper amount of grease? Sure, the bearings aren't going to reach their L10 life, but that also contributes to reliability and uptime. A $300 bearing failing in the middle of the day might not be so expensive on the part, but what are the results of that? Are we going to have downtime? Are we going to have to pull apart the machine? Is there going to be other equipment damage? Are we going to start to damage various other components? So we really want to have a way to verify how much grease we're putting in. So back in the early 1900s, a gentleman by the name of Strybeck developed a curve known as the Strybeck curve. And this tells us the optimum lubrication status. And essentially what it is a point where friction is at its lowest coefficient. Outside of that ideal quantity, we start to increase friction, increase wear. As you can see on my screen here, as you see my cursor, as we add grease into a bearing, we're going to reduce right down to what we call this mixed status, where the frictional coefficient is at its absolute lowest. If we keep greasing that bearing, we're going to move into the hydrodynamic status, where we start to increase the friction, increase the wear. So there really is that sweet spot. And how do we measure this? How do we know that we're hitting that ideal spot every time when we go out to grease our bearings? Well, in the past, and for most OEMs, there's different calculators and formulas. So SKF has a method. Based on the bearing dimensions, they'll tell you how much grease to put in the bearing, whether it's a side or an annular replenishment fill. And then the interval at which we grease a bearing, that can also be run through a calculator. But then we have to start to account for all these various factors. So everything from bearing speed and size, temperature, vibration, moisture, condition. And what that equates to is this nice equation that we've got up on our screen, and that's going to give us the ideal time until next relubrication in hours. Now, if we get one of those variables wrong, that's going to throw off the whole equation. So you can see it's not a fine science. We can't just take these numbers and start to spit them out and say, okay, we're going to grease that bearing every 2 or 3 weeks. We want a way to verify this and make sure that that bearing right here, right now, is getting the proper amount of grease. So what if we had the ability to do that? Well, we do this day and age, and it really comes through ultrasonic lubrication. What that's going to do is tell us exactly how much grease to add, when to stop, and it's going to provide feedback with each injection. So as we put grease into that bearing, or a luber shoots grease in that bearing, the technology is going to give us that instantaneous feedback, monitoring friction levels, telling us if we're over or under lubricating, and really hitting that sweet spot. A couple shots on the screen. The top one is from our industrial matrix software, which I'll get into. And what that does is an online system. It'll trigger lubrication based on warnings. And at the bottom is a portable ultrasound detector. So it greases, and that it actually follows, if you notice from a few slides ago, that Strybeck curve, where we grease, go down, down, and as it starts to come back up, we're getting into that over lubrication status, or at least pushing our way towards there. We cut off lubrication. So this technology is really following what we've designed over 100 years ago and dictated is the lowest frictional coefficient. So quick poll you're going to see pop up on your screen just to get a feel for ultrasonic experience for everyone that's on the call. So a couple different questions for you. Have you used ultrasound for any of these applications? Have you used it for greasing bearings, trending bearing health, other application? And then finally, are you Cat 1 certified? Have you done training? You can select multiple. So any that apply to you up on the screen, go ahead and tick them off. And if none apply, just go ahead and click none of the above. So I'll fill that out as well myself. And then once you're done, go ahead and submit the vote. I'll give a quick second just for those numbers to come in here because there are quite a few questions. So it looks like based on the feedback we've got maybe a quarter of the audience has used ultrasound to grease bearings. So thanks for joining us today. Hopefully you're going to pick up a lot. Some have used it for trending bearing health, and looks like a small percentage have done it for other applications, and some haven't done it at all. We've got a couple that are Cat 1 or ultrasonic certified. So thanks for that feedback. Now, why ultrasound? Why do we want to use this technology? Ultrasound has quite a few benefits when we talk about monitoring assets. First of all, and we'll get a little bit more into it, the sound is very localized. Ultrasound working at this high frequency, the sound doesn't like to go out very far. We say it doesn't like to go out and play with others. It's very sensitive to small changes. It also gives us a perfect indication of what's going on with friction, also very repeatable, consistent, and some of the devices give us the ability to hear the injection. So maybe some of the more old school guys, they like to put on their earmuffs, go out with the detector if you've ever seen that, and they can actually listen to the grease go into the bearing and do it by ear. We can also take ultrasound like in the picture on your screen there, and we can pair that up with an auto luber. And what that allows us to do is autonomously lubricate the bearing and give grease without the human intervention or the human touch. The system starts to do it automatically. So what happens when we grease with ultrasound? Again, we're measuring the frictional component, and we use a scale called decibel per microvolt. When we add grease to bearing, we're going to expect 3 things to happen. We want that feedback. So the dB levels go down is the first thing that can happen. Well, that's good. We're reducing friction. We're typically going to keep greasing until they rise back up again. Or if the system's online, we're going to hit it with grease, expect to see those levels go down, and then cut back up. Now, the second thing that could happen if we grease a bearing, the levels are going to go up right away. Well, in that case, we're going to stop because we know we're going in the opposite direction. We're increasing friction. We're not going to grease that bearing anymore, probably already in an overgrease status. And then finally, the third thing, what if the dB levels don't change? Well, there could be a lot of different factors. Maybe we're not adding enough grease to modify the friction level. The grease isn't getting to the bearing, our grease gun or our luber is empty, or another issue that's going on. That is probably the most important thing that we can get out of an ultrasonic system, because if we try and grease a bearing and we're not getting grease in there, we need to know that. Otherwise, what are the consequences? Well, that bearing is going to run dry, metal on metal contact. It's going to fatigue the bearing. Eventually, it's going to fail prematurely. So When we talk about ultrasound, where does it fit in? For those of us in the audience that have had some experience with other condition monitoring techniques or even ultrasound, if we've worked with vibration before, ultrasound really works in conjunction with other technologies, predominantly vibration. And really where it fits in is if we look at on the screen, these are the 4 stages of bearing failure. As a bearing starts to progress through failure, it'll hit these different stages, and technology will tell us what's going on at each stage. So for stage 1, very high frequency. That's what we're going to detect with our ultrasound. Very minor subsurface defects on the bearing, and usually we can improve that with lubrication. So as that bearing starts to get loud acoustically, we can grease it back down. Doesn't mean the bearing's failing, it just means that that bearing is in need of something. Now, if we let that go or if something happens to that bearing, we start to move into the progressive stages. Stage 2, still in high frequency, starting to appear in our acceleration and velocity technique. That's where if we pulled apart the bearing, we might see a little bit of damage or spalling in the race. And then eventually the bearing's going to degrade even more if we leave it, get into stage 3, stage 4. Good analogy I like to use is your car brakes. So you're driving down the road one day and you hit the brakes and you hear that very high pitched squeal. What that is the early indication. Your pad is worn down to a point where you got that little wear bar that's touching the rotor. It's going to produce a very high frequency event. Now, what happens if you leave that and you don't replace your brakes? Well, eventually you're going to get more pad wear down. You're going to get more metal on metal contact, and the frequency of that sound is going to start to come down in the audible range to a point where you get that metal on metal grinding, and it's just this low rustling sound. Same thing with our equipment. It's going to start at that high frequency squeal and then just come down in the audible range as the damage progresses. If we look at the PF curve, I'm sure most people on the call are pretty familiar with what the DIPF curve. There's a lot of different iterations out there, but we really put ultrasound at the front. So after we have the installation and before the proactive domain, ultrasound fits in there because as a bearing starts to need lubrication, we can grease that out using ultrasound technology. Doesn't mean the bearing's starting to move into the failure curve. It just means that the bearing's in need of something. It also monitors the condition of a rolling element bearing. So if we're greasing a bearing, it goes up to a certain dB, we grease it back down. We go out next month or next week, or the online system picks up that it just keeps climbing. That's going to tell us the health of our bearing. So we kind of use the tool as a twofold and a technology for 2 different benefits where we can grease and we can monitor the condition. Now, as we progress down the PF curve, this is where we pick it up in our vibration techniques. Going back to the last slide, we'll start to see a defect. If we find it in ultrasound, acceleration, velocity, eventually it'll start to create a heat signature. By the time a bearing creates a heat signature, it's getting pretty close to failure mode. And then eventually it becomes loose, your clearances go away, and then you do damage. So you really want to deploy technology on the PF curve to find these defects before they become a real problem. And if you're looking at stuff like heat, a lot of different places will go out with a temp gun and shoot heat. You're at the advanced stages of failure or almost in the failure domain by the time you pick it up with your heat. We say it's typical to discover a defect with ultrasound and then trend it to failure in vibration and heat and thermography and other technologies, which is really true. It's that early indication and indicative of lubrication. So I'm going to talk a little bit about ultrasound. I won't get too in depth. For those of you interested, as you start to go down that road, I definitely encourage you to do your Cat 1 certification. This technology is becoming more and more beneficial outside of even what we're talking about today. But I'll give you a brief background and justify why we use ultrasound. So in our world, 3 different types of sounds. The first one's infrasound. Anything under 20 hertz, stuff that we can't hear as humans, but we can maybe feel. From there, 20 hertz up to about 20 kilohertz. Now, depending on your age, that 20 kilohertz starts to drop down. So it can be down to 16 or 18. That's the audible range. That's where we as humans live, breathe, hear. That's our entire environment. Anything above 20 kilohertz is considered ultrasound. So when we talk about these sensors, we're listening above that 20 kilohertz in the ultrasonic range. Now, ultrasound is produced by the vibration of molecules in any elastic medium. So that could be gas, liquid, solid. So it's airborne, structure-borne. It's all around us, that frequency range. We just can't hear it. What we do with this technology is we use the acronym FIT. So if anything produces friction, impacting, or turbulence, we're going to detect it with ultrasound. When we talk about condition monitoring and lubrication, we're really looking at the friction and even the impacting. That's what the technology is going to tell us. But we can also use ultrasound outside of bearing health lubrication. It has been used for air leaks, steam trap monitoring, checking valves, and assessing tightness. That's where you can put a transmitter in an enclosure, seal it up, and actually scan around. If the sound gets out, then ingress can get in. You're not completely airtight. So it's a very, very versatile technology, and it's really starting to progress in the past few years. So what does sound do? Well, it travels as a wave, works over a wide range of frequencies. The behavior of the sound wave really does vary depending on the frequency. Now, sounds all around us can go through materials, reflect off them, and then the amplitude increases or decreases with distance. If I'm speaking to you, if I'm 10 feet away or 3 meters away, and then I move up to 5 feet, so I half the distance or 1.5 meters, I'm going to get twice as loud. My amplitude's going to pick up. Same as if I start to speak in a higher tone, the pitch gets closer together, those sound waves are going to come in closer. They're going to become more localized. So higher frequency, shorter wavelengths, lower frequency, longer wavelength. Again, a good analogy, I always like to go back and relate this to the real world. As far as music goes, you're sitting in your car, you're at a stoplight, right? And you have your windows up. The guy next to you, he's in his car, his windows are up. Now he's listening to stereo at a very loud volume. In your vehicle, you're not going to be able to maybe hear those high frequency notes, but you'll hear the low rumble, the bass, the boom, boom, boom. The reason that is because lower frequencies travel a lot further. They can go through materials, they can disperse. The wavelength is a lot longer, so they can penetrate and they have a lot more energy to travel further. Those high frequencies, though, they're going to become blocked out because as we move up in the frequency range, barriers can really block that noise, meaning that it's far more localized. That's why if you blow a dog whistle in a room, if you're on the other side of the door, you might not be able to hear it, but if you start banging on a table at a low frequency, you'll probably be able to hear it. How do we measure sound? Well, sound is measured in hertz. That's the international standard. For those of us in North America, we also use CPM or cycles per minute. They're very interchangeable. So when we talk about sound, typically we talk in hertz, but when we get into vibration and diagnosing, we'll also relate to CPM. 1 equals 60, just for those of us who need a conversion. So again, why is wavelength so important? Like I said, the higher the frequency, the shorter the wavelength, meaning the sound is far more localized. Most ultrasound sensors that we use, the one we use here at Industrial Matrix, is calibrated to 38 kilohertz. At that frequency, the wavelength is very, very small. It's only about half an inch or a couple millimeters. For comparison, my voice that I'm speaking at right now is in and around 100 hertz. What that means is the wavelength that I'm propagating is about 11 feet in length. So there's a lot of a difference in the wavelength as we move up in that frequency span. What that all equates to is when we take an ultrasound sensor, we put it on a bearing, we drill and tap it, we magnetize it, epoxy it, we're only really measuring within about a 1 foot or a 30 centimeter diameter. So unlike vibration, the signal is really unaffected by events further away. If there's something going on further down the machine or on the other side of the motor or the pillow block, the ultrasound's not necessarily going to pick it up as it reads that particular bearing. It's just going to focus on what's in front of it. Again, a quick chart just to really bring that point home. Again, I said I'm speaking around 100 hertz of frequency. My wavelength is 11 feet. If I go lower, the wavelength gets a lot longer, and then higher up in the frequency spectrum, all the way up to 38 kilohertz or 38,000 hertz, it's only about 0.3 inches, so very small wavelengths. So what does ultrasound do? Well, it measures friction in a rolling element bearing. Again, like we said, at very high frequency, meaning the sound's very localized. Events far away, it's not going to detect, or it's not very good. And what that's going to really do for us is tell us exactly when to grease a bearing. Again, we're measuring friction. When we add grease, we're measuring that frictional coefficient, and that's really going to indicate to us if we're under or over lubricating or giving perfect lubrication to our bearing. What that means is we're giving our bearing that nourishment exactly when it needs it. To bring you back to the first slide. So just to close off, I'm going to talk about some different types of equipment, just to give everyone and paint a good picture for what's out there, because there is a wide variety of ultrasonic equipment on the market for condition-based greasing. Each has its own tangible benefits and disadvantages as we start to look at what's available out there. So kind of 4 different options that I put them in: handheld basic, more advanced, and then online manual and online automatic. So let's talk about some of the basic ultrasound equipment. If you've ever seen a technician out there greasing with ultrasound, typically they strap onto the grease gun. There's ones by SKF, SDT, UE, Sonophone, some other manufacturers in there as well. And what they typically do is they work off route. So there's no software associated. What you see is what you get. As you put that sensor onto your bearing housing, or if it ties into a grease adapter, you can pick up the ultrasonic through there, put it on the grease fitting. It's going to display on the screen either a digital readout, or some of them have bars on them. And every time you add grease, you're going to look at if the numbers go up or go down. They usually come with headphones as well, so you can listen to that bearing taking the grease as you put it in. So very basic, easy to use. Open up the box, take this equipment, go out, start greasing bearings with it, and you're going to justify what you're doing. Now, we take that and we build off it. There's some advanced ultrasound equipment. What this equipment does now is it starts to work with a software package. We can load in bearings, we can anticipate grease quantities that are loaded, and some of them will even guide the user when to grease and when to stop. So it'll just say grease, and then it'll tell them when they've had enough. All of this data is going to be saved, and then you can go back to computer, plug it in, export it, and trend and analyze what you're doing with your bearings. So it takes the basic equipment, it introduces the data logging or the ability to analyze what's going on. And then finally, online systems. These are really the newest technology to come to market as far as ultrasonic lubrication goes. What they do is provide real-time monitoring. They're going to give you lubrication status and bearing health, and they'll communicate with auto lubers. So instead of the human intervention where you have to go out and visit that bearing with a portable ultrasound instrument, these will automatically grease, or they can trigger a manual lubrication, and they're going to give that bearing grease exactly when it needs it. So if you're doing a lube route with your ultrasound every 4 weeks, you might let that bearing might get dry by the time you get out there. These type of systems will always be listening to the bearing and give it grease the exact second it needs. We say it's the first iteration of a bearing repairing itself. So here at Industrial Matrix, our product line is called the Lube Matrix, and this is where we take the ultrasound, we pair it up with an auto luber. We utilize radio communication for very high portability. We'll dashboard that online and some browser-based software. And once we set the system up, it is very autonomous. It's going to be greasing these bearings with or without human intervention. All you really have to do is configure it, and then you'll look at that bearing every so often and check in on it. Now, how does it work? So PF curve, we hit the ultrasound there. We have the sensors, we have the lubers installed. They're communicating via radio frequency up to the cloud. And what's going to happen is when that bearing starts to run dry on grease after we've baselined it, it's going to call for lubrication. We're going to program and get that auto luber to fire, delivering enough grease to settle that bearing back down to baseline until the next episode. So if we're greasing a bearing every 4 weeks, for example, we might grease it every 3 or 4 days, but just a little amount every time that it needs it. And what we say is that is really an early iteration of a bearing repairing itself. So now we're starting to take the human factor out of it. We configure it, we set it up baseline, and the luber's doing the work. We're also getting feedback in the system. So what are the benefits? Obviously the convenience, right? We don't have to go out, we don't have to grease bearings, we don't have to have a guy with a grease gun. It really is an ideal solution for remote, acritical assets, stuff that we can't necessarily get at, but the cost of failure is quite high. The cost of failure, we want to reduce downtime. That's where we tie in precision lubrication. And then from there, we're going to help to create ROIs and show how this technology is going to help you reach that L10 of your bearing. We can scale the system up as well. We can get up to 100 bearings on a single controller. Line of sight using radio frequency is really good. We're almost 10 kilometers line of sight. Realistically, it's going to be less as we get stuff in the way, but it's very far range, a lot better than Bluetooth or Wi-Fi in some instances. And then finally, not only are we greasing, we're also trending bearing health as well. So when that bearing finally does start to fail, we're going to have indications for that. What do we do as far as the Lube Matrix system? Well, we have two offerings. The first one is a single point lubricator. What we can do is tie two ultrasound sensors into one single radio. We also tie in two lubers. Very portable. We power the radio, and then this will send it back to the main controller. So if we're in a plant and we want to monitor one pump down the way, and we want to monitor a fan up on the roof for the Lube Matrix, we have the ability to do that because we can modulize the system and move it around. It's not all hardwired back into one main system or one main box. What does the infrastructure look like? Well, we have a main receiver that connects to a Wi-Fi router with a global SIM card. So we use cellular to send it up to the cloud. That's going to come in a small enclosure. From there, we can get up to 50 radios on one controller. If we go above that, we can just add another controller. And then each radio will speak to two ultrasound sensors and two lubers. And then finally, we can also tie into a multi-zone system. So I'll play this animation. Say we're listening to all four of these bearings with ultrasound. Just that second one from the left starts to rise up, indicating the need for lubrication. We can then install these brake valves that will open up, deliver lubrication to just that one bearing, settling it back down to baseline and not greasing all the other bearings in tandem. Typically with a central lubrication or multi-zone lubrication system, it's just going to push grease blindly to these bearings. Now we can add some science behind it and make sure we're not over-greasing some, under-greasing others, because again, bearings needs change depending on their workload and their demand. So we take the Lube Matrix, we marry it up with what we call our asset matrix. And what we'll do is when we configure a system, we'll design what we call an asset card for each particular piece of equipment that we're putting Lube Matrix on. And then we're going to start to dashboard certain metrics. So we're obviously alarming around the bearing. So if that bearing moves into failure, we're going to get alarm. We're going to get warnings as well, and then even critical alarms. And then we'll start to trend things like how much grease we put into that bearing, how many times have we lubed it, if we have had successful lubrication. Say we grease that bearing, it doesn't grease successfully, we'll return an unsuccessful lube and then send a notification. So it really is full accountability. As you can see on your screen, even little things like keeping track of how much grease is left in the luber. For anyone who's ever worked with auto lubers, they know that sometimes they run empty, nobody checks on them, and you have an empty auto luber sitting there for days, weeks, months. We're going to keep track of that. And then as well, when we fire grease in that bearing, we have the ability to feed back from that luber. So we're going to tell the luber to grease that bearing based on condition, and then that luber is going to send a signal back saying, I actually grease that bearing. So we know what's going on at all times with our bearings and with this system. Again, just another screenshot here. With the system, we do live dashboards. We'll send notifications, whether it be text or email or even a daily report. And if anything goes into alarm or anything goes wrong, then we're going to be notified pretty instantaneously. Finally, I'll play an animation. This is live data from a lube matrix system. As you can see, we're taking a sample every minute here. We've baselined it at the yellow. Eventually, the bearing is going to get loud, come up into the yellow zone, and you're going to see an A appear on the graph. That's going to indicate that it's been an alarm and the auto looper is fired. Once that auto looper fires, what we're going to expect to see is that bearing come back down below baseline, run smooth again. Now, as long as that bearing is healthy, it's going to repeat that throughout the life cycle of the bearing. Eventually, as it becomes to the end of its L10 life and that bearing starts to fail, we're going to see those levels start to go up. Once we hit that red zone, then we're going to know that that bearing's moving into failure mode and it's time to start planning the replacement. Or if grease doesn't take, say we fire the grease in there and it doesn't settle down whatsoever, we'll lock up the lube or send a notification saying, okay, we tried to grease this bearing, we've calibrated it properly, it didn't take any change, something's going on. That's going to let us go ahead and check it. So to finally close off, I'm just going to talk a little bit about what we do here in Industrial Matrix and what our philosophy is. So it really starts with our predictive maintenance platform and or our Lube Matrix platform. So that's again where we deploy wireless sensors. They speak to the cloud. We'll give you live dashboards, alerts when something goes into alarm, and that's going to allow us to take corrective action. In the case of Lube Matrix, when something moves up into alarm or warning level, that's going to allow the luber to take corrective action if the bearing's not in failure. And we take that and marry it up with our asset matrix system. So we have the ability to do a plant survey where we can digitize all that asset data. If we're monitoring anything, that will already be done for you. That's going to give us the ability to know exactly what equipment we're installed on and what equipment's in our plants. We can then look for crossovers and motors, bearings, pumps, gearboxes. We can also directly send RFQs to suppliers, and that's going to help to reduce downtime as well. If we know what we're monitoring and the condition of it, we marry those two together, that really starts to paint the picture. Now, we realize that to go out and install a bunch of lubrication equipment in a plant, everyone has different abilities. So we want to make this successful, and that comes with our path to success. So we get involved right away. Most of the equipment is plug and play, or we'll come on site and help to do the install, the configuration, the tuning, make sure that everything is set up. If you buy a bunch of equipment and it's never configured or installed properly, you're not going to get any value out of it. So we really want to make sure that we help you with that value. And then from there, we'll do a little bit of training. We won't do the full Cat 1 ultrasound program, but we'll make sure that everyone who's bought into the program and who has a stake in it knows what's going on, how the technology is working, how it's set up, and what it's going to do for us. From there, probably the most important value add is we'll do weekly meetings. So we have a customer success team here at Industrial Matrix. Once we online, onboard, and configure a system, we'll meet every week for 15, 20, 30 minutes, however long it takes. We'll go over the data and make sure that everything's set up properly, that everyone knows what's going on. If something moves into alarm, we're going to work with you being ultrasound and vibration certified analysts here on staff. So you're not doing this alone. You're not installing a system and just saying, I hope it works. No, you're getting that hand holding where we really get you to the finish line. From there, the goal of any condition monitoring system is to create value. We're installing these assets and buying these devices so that we can go around and save assets from downtime. That is the ultimate goal of any predictive maintenance program. We want to work with you and create value. We want to show you what you were doing before might not be as good as what you're doing right now, and there's always going to be a dollar value associated with that. If you're having a particular bearing failed due to poor lubrication, we're going to show that if that bearing's lasting 2, 3, 4 years, now we're getting 5 or 6 out of it. That's value created there, and it's not going down in the middle of the day and causing a lot of chaos. And then finally, we want to expand. That really is the goal, is to get on more assets, really hone in on the PMs that you're currently doing at the plant. Finally, We can take an entire schematic of the plant. We can upload that into the software. We can color code each asset red, yellow, or green based on the current condition or lubrication status, visually giving a representation of what's going on in the plant. So that's it for the presentation portion. I want to thank everyone for hopping on and joining us today. Hopefully you picked up a little bit, and from here, if you do have any questions, I'll encourage to utilize the chat feature there. Dan's going to pop back on there and just go through some of the questions that have come in throughout the presentation. But again, thank you, everyone. You're on mute there, Dan.
There we go. I got two mute functions here. So thanks, thanks Ken for that informative session there. I got a lot out of that. We got some questions coming in about some greasing and ultrasound. So I'll get started. Our first question is from Matt, and he asks, will the grease exceed the capacity of the bearing? Is that likely to happen?
Yeah, that's a really good question. So pertaining to the lube matrix system, what we'll do when we install the system is we'll actually take a little bit of science in behind it. So we'll put in the specific bearing number that we're installing on. We'll run it through and cross-reference it with what the OEM recommends. So SKF has a particular calculation for the replenishment quantity, and then we'll calibrate the luber to deliver 20% or as close to that as we can get of the calibrated replenishment quantity. The reason why we do that is 20% seems to be the magic number. When that bearing starts to go up in ultrasound, it hits a lube cycle. That's going to be enough grease to either make it keep going up or to drop it back down. So everything will be dialed in properly for that particular bearing. Because like we said, all bearings are different, right? No two bearings have the exact same identical needs. We'll configure it based on the bearing, and then we'll let the technology take over from there. If the decibel levels don't change, we don't add enough grease, or we add too much grease and they don't drop down, then the luber will lock itself, send us a notification, and then the technician can go in and analyze alongside with us to determine why that bearing's not changing, why we're not modifying the friction. So great question. I really like it. But yeah, using the technology is really the way to ensure we're not over greasing bearings, which is a big problem out there.
Okay, great. Thanks, Ken. The next question we have from Trevor is there a specific decibel number that will tell me if the bearing is good or bad?
Great question. I've heard that one quite a bit before. Is there a magic number? Should my bearing be at 30 dB or 35 dB? How do I really know? So when it comes to ultrasound, because each bearing's different, there are no standards. There's no ISO standards. If you're familiar with vibration, then you know in the lower frequencies and the velocity, you can reference an ISO chart. It'll tell you what's acceptable, what's unacceptable. Ultrasound is purely based on condition. So each bearing is going to behave different depending on the load, the work, the overall life cycle of that bearing. We can, however, learn where to baseline a bearing. After we lubricate the bearing, maybe on our time-based schedule, the first few shots of grease, we want to kind of determine the highs and the lows. So where a bearing can go up to, the minimum point that we can grease it down to, and then we're going to determine baselines and where lubrication triggers should be assigned. So it is really a discovery of the bearing. We're learning about the bearing as it's telling us its history and where it's at. Now, going back to the 1970s, and for those of you who are familiar with ultrasound, there's a NASA study. It's fairly, well known in the ultrasound and condition monitoring ring, where NASA scientists and engineers, they did a study and they determined some rough guidelines, which we still use to this day. So from where we baseline a bearing, an 8 dB increase is going to indicate a need for lubrication, 16 dB for, a warning or a yellow band alarm, and then a 24 dB increase from baseline is going to tell us that we're getting into a warning status on that bearing, could potentially be in failure. Now, again, that's going to change. Lower speed, we're going to tighten those up quite a bit. If it's higher than our typical 12 or 1800 RPM, we might expand it out quite a bit. But we do have a lot of guidelines to go off. But when it comes to ultrasound, it really is about baselining that bearing and looking for that change over time, and then discovering what happens as we grease it. Great question. Thanks, Trevor.
All right, we got another interesting one here from Kamar. Kamar asks, can your system be configured to trigger an alarm in local controller or even to trigger equipment shutdown if vibration becomes excessive?
So you're talking about more of a protection system. So we definitely have the ability, and we didn't really get into it in this presentation, but we can discuss further with you, where we integrate with what we call our drives matrix. So we can take this condition monitoring technology and then communicate to PLC. So right now we're taking the data in, we're listening to it. We also have the ability to push data out. So if we want to go back and look for, if a machine gets beyond thresholds, where we can trigger a shutdown and then a notification, that's absolutely possible. And that's really where condition monitoring and technology is going. It's giving us the ability to let our machines control themselves based on their needs at that current time. So thanks for the question, Kumar. It was a good one.
It was indeed. Next question we have from Brian. Brian asks, what type of technical or personnel training would be a nice complement to your monitoring program?
Kind of technical training would be so obviously, when we talk about utilizing the ultrasound technology, it is becoming more widely recognized. So within the rounds of ultrasound, there are different certifications. We have our Cat 1 certification, and then the level 2 that's out there. So I would really say, getting started, and as you get into the technology, obviously becoming certified and being able to know what's going on and behind the background will give you a better understanding. Again, I'm going to loop back to what we do with the Lube Matrix. This is where we come in because we've been dealing with this technology for quite a number of years. We've got to know it quite intimately. So that's where we're going to help you and bring you up to speed. And if you're like me, you kind of learn by doing. So by looking at what's going on, analyzing the data, determining where your bearing's healthy, when it needs attention. That's really what's going to get you to the next level and help you learn this technology. So the technical and the hands-on, you marry those together, and that's going to really paint the picture for you and help you to understand what's going on.
Okay,
Thanks for the question.
great. Yeah, thanks, Brian. Great question. Another question here from Peter. How does the ultrasound sensor need to be, how far does the ultrasound sensor need to be to the bearing, or how close can it be? Can I attach it to my remote grease line?
Absolutely. Great question, Peter. This is one that comes up quite a bit when we talk about ultrasound and over the years working with different guys getting on board and girls with ultrasound programs. So going back to what we talked about, ultrasound, it attenuates quite quickly, meaning the sound's very localized. So if we look at a remote grease line, sometimes it'll come out of the bearing, might go to a rubber fitting, and then it'll go back to metal. We get into this a lot in the Cat 1 ultrasound certification, where they talk about the specific acoustic impedance of different materials. So as we transfer sound from one material to the next, or if we go over a distance, that sound's going to dampen, it's going to be deadened. So say, for example, we've got a rubber line that comes out and then goes in a metal line for another 3-foot run, and then you're trying to take an ultrasound measurement. You might get something off of it, but you're not going to get great data off that because that sound at that high frequency, it's not going very far. So how close does it need to be? Ideally right on the bearing or on the grease fitting. As close as we can possibly get to the bearing, the closer the better. So even when we do condition monitoring with ultrasound, if we use a portable or install an online system, we want that sensor as physically possible as we can get to that bearing. That's going to ensure that we're getting the best reading and that we're able to diagnose what's going on with that bearing. So thanks for the question, Peter.
Okay, next one's more of an administrative question. There were a few people who joined a few minutes in. So the question is, I missed the beginning. Can you send me the link to watch it later? Yeah, so when we end this webinar, the recording will be converted to a viewable file, and it will automatically be sent as an email attachment to all of our attendees for today. And if you'd like to get a downloadable PDF version, reach out to Sam, Ken, or myself, and we'll send you over a PDF version.
Fantastic.
All right. So next question that we have here is from Harpreet. He asks, I have a vibration program. I already have a vibration program. How does ultrasound complement my existing program?
Awesome. Thanks, Harpreet. So vibration is definitely a more predominant technology when we look at what industry is adapted as a whole. Vibration has the ability to tell us, quite frankly, a lot more what's going on with our equipment post ultrasound. Ultrasound, if we put the sensor on a bearing, it's really just telling us the bearing health, right? What's going on, if there's any impacting, if there's a frictional component where vibration is going to tell us, what else is going on with the machine. Now, where ultrasound really fits in, it is the same type of technology. They're all piezoelectric sensors. Vibration's getting into this newer MEM sensor technology that is becoming a lot more predominant out there in industry as well. What ultrasound really does is it gives us the added value of sampling at a much higher frequency. What that does is it filters out the low frequency noise. So we're not listening to any physical movements. And ultrasound really allows us to narrow in if we're trying to monitor a bearing. So we're going to pick up bearing defects a lot quicker. Harpreet, if you're a vibration analyst, I can equate ultrasound to a demodulated, high frequency envelope, kind of shock pulse spike energy technology, but it has a much lower noise floor. So we're going to pick up that friction and impacting a lot better. Ultrasound really fits in that, as going back to the presentation, that stage 1 to stage 2 bearing failure. And we're typically going to see it appear first in ultrasound and then eventually in vibration. So we say fine with ultrasound, trend to failure in vibration. Two of the main advantages for ultrasound where we start to exchange that with vibration, and if you've ever worked with the technology, you'll know there's a certain cutoff speed. A lot of vibration sensors, some are around 600 RPM, some of the piezoelectric ones can go down to about 100 RPM. But when you get into slow speed and slow rotating assets, vibration isn't going to give us good data. That's really where ultrasound starts to step in on the condition monitoring front. So we can actually replace it with vibration at a certain point. Also, if we have equipment that starts and stops, if it moves very intermittently, then vibration needs time to take a sample to build that. It can take you, if you want a high frequency or a high resolution sample, it can take you, 5-10 seconds. If you just have these little spurts, ultrasound is kind of a listen only device, and then we filter down from there. So it'll allow us those short durations. But great question. So just to summarize, ultrasound on condition monitoring will find defects first, tell us lubrication, and then it will replace vibration in those low speed monitoring applications where we're not getting good data. Thanks, Harpreet.
All right, thanks, Harpreet, and great explanation, Ken. We had another question here from Andre. Andre asks, why are you using SDT ultrasound solution sensors? I wonder who Andre represents here. Yeah, I can field that one. So with our system, we can use basically anything that's on the market. We're currently using SDT sensors as it's a pretty good quality product so far, and we're able to meet or they're able to meet our quick demands in terms of lead time. And we've had some pretty good track results with them. So that's why we're using SDT right now.
Absolutely. And we talk about repeatability. I mean, we've configured our system and nod to Andre to use the best technology out there. There's a reason why we use Perma brand lubers, because they can give us that feedback. They're very portable and easy to use, and we use good ultrasound technology. And it really relates back to that. If you use bad products or cheap technology, it's not going to function properly. You need a good calibrated sensor to an ISO standard that you can ensure that reading that you're getting is 100% verified and vetted. So you need to use good equipment. There's a lot of equipment out there on the market these days, some from overseas that doesn't quite function as well. And you got to ask yourself, are you really going to trust your reliability or your condition monitoring program to something that you've cheaped out on, or you've bought as an off brand that has no traceability, no standards? So it really starts with using good equipment. Absolutely.
All right. Okay, so it looks like we're coming up to our last question here. This one's from Thomas. Thomas asks, will this work on a cargo ship wherein residual vibration is always present? Residual vibration comes from other machines operating in the vicinity.
Yeah, great question, Thomas. So going back to how ultrasound functions, if we put an ultrasound sensor on a bearing, it's not picking up on that. When you talk about residual vibration, you're talking about physical movement, right? You can feel the floor shaking, the machine shaking a little bit. The ultrasound doesn't care about that. We filter around a very high frequency. So what we're really listening to is that frictional component, those little small impacts in a bearing. Even if that whole machine is physically moving, say for example, outside of your application on a cargo ship, if we're on a pillow block on a fan, right, and that fan is imbalanced, it's going to pick it up in the bearing because that bearing is going to be moving around and we're going to have tolerance issues. But for the most part, the ultrasound is not going to pick up on that physical movement or any residual vibration, again, because it's at a high frequency. When we look at vibration that may or will pick up that residual frequency, vibration sensor typically operates in and around 1 to 10 kilohertz, depending on how you filter it down. That's in the audible range. That's in the lower frequency range. So it's going to pick up on those events. That ultrasound way out at 38 kilohertz, and then we filter around that 38 kilohertz. It throws all that low frequency stuff away and just leaves us with a clean representation of that particular bearing. So to answer your question, sound attenuates very quickly, high frequency. We're not focused on any of that physical movement. We're way up listening to the squeal and the whine of that bearing that we're monitoring.
Where we might see residual vibrations, and there have been instances with a few of our customers where we have seen vibrations from one machine showing up in another, is when we're using accelerometers and temp vibe sensors. And usually that we've actually used that at a customer to identify there was an issue further up the line from a piece of equipment that was being monitored. Vibrations were coming from a piece of equipment that wasn't being monitored. The way this was determined was we started picking up the vibrations, made recommendations that the maintenance team go out, take a look at that piece of equipment that had the sensor on it. They realized, oh, this thing's, it's running fine and the PMs are up to date on it. And they started looking around, and that's when they realized, oh, this machine upstream was actually getting close to failure, and our sensors were picking that up. So that can happen. And again, as Ken points out, it depends on the type of sensor equipment that you're using. If you want to get the early detection, obviously go with ultrasound, and then depending on what you're looking for, we would address the type of sensor used accordingly.
Yeah,
So.
good point there, Dan. And if you were using ultrasound in that application, you definitely wouldn't have picked that up. And that's where, when we talk about condition monitor, there's no one technology that's going to solve all your needs. As you get in and you start using, whether it be vibration, ultrasound, oil analysis, thermography, temperatures, all of those condition monitoring techniques paint the picture. And if you've ever thought or gone in the direction that one type of technology is going to tell you everything you need to know about your equipment, that's usually not the case. Different technologies better for different applications. However, you need to really marry it up. And that's how you build a good reliability program, where you're using different types of technology to analyze and determine the status of your equipment and how close it is to failure or how much degradation you have there. And then that allows us as maintenance professionals to start to plan and mitigate downtime, because then we know the stuff's coming up. So yeah, that's a great case of a vibration sensor, not on a machine, but that machine's not bad. Something else down the line is bad.
Good stuff. Okay, well that's it for the questions entered so far. We've got about 3 minutes left in our scheduled time. So if anybody who's left has anything else to ask or anything they want to talk about, now's the time to get it in there. Another point I wanted to talk about, Thomas's question about using on the cargo ships. I think the ultrasound sensor setup itself would work. There's also the aspect of the system itself. With our system using cellular communications instead of an internal network, basically anywhere that there's a solid cell signal, we'll be able to send the data from the controller, which pulls the data from the sensors up to the cloud. And we'll be able to report out. So we've had some customers looking at putting sensors on mobile sawmills, for example. So there is definitely the option to have more of a mobile setting for our mobile environment for our system to work. All right, so I think we've calmed down on the questions and comments so far. So thanks everyone for your attendance. Our information is in the link provided, and as I mentioned earlier, we will be auto emailing the recording as soon as we're done here. And if you have any other questions or would like further information or would like a downloadable version of this webinar, please feel free to reach out to Ken, Samuel, or myself.
Fantastic. Well, thanks for that. I saw one more pop up there from Brian there. As you close off, Brian, I'll hit you an answer when I chat with you next for your question up there. So we've kind of run out of time, but yeah, thanks everyone for joining us today. Big thanks to Dan for hosting and doing all the hard work in behind this, and for Sam for doing the technical setup, and for making sure that everyone was able to find us at the right place at the right time. So thanks, gentlemen. This has been a lot of fun, and we'll definitely be doing more. So we'll communicate that as the months come on. On that note, everyone have a great day, and we'll talk to you real soon.
Thanks, everybody.
All right. Bye now.
Bye.